K will be less than Ki, between initial and final state should be conserved. And now there's an object 1, there's an object 2. It is at rest. So let E equal to 1. Let's see the in center of mass frame how the system will be. So the center of mass of system, let me give star mark. Here the center of mass will be moving with a velocity uc. And we know after collision, what will happen is the first body will come to rest and the second body starts moving with a and this will come to rest here. The first body will come to rest. Second body will move with the initial velocity of the first body. Let's check the center of mass thing. So first, let me calculate that velocities here. So from conservation of momentum, or you say, sir, how do you can say, we'll do one thing, I'll write V1, V2. I don't know what will happen. Let's calculate first in ground what will happen. Applying conservation of momentum, M1U, MU is equal to MV1 plus MV2. Will agree? So therefore, U equal to V1 plus V2. Applying quotient of restitution, V2 plus V2 plus V1 plus U minus 0. E equal to 1, so V2 minus V1 by U, or U is equal to adding up these two. So how much will get? V2 equal to U and V1 0. So what is the conclusion now? After impact, what actually happens? The first body will come to rest. And the second body will move with the velocity of the first body. This is before collision. This is after collision. Okay, let's see in center of mass how the system will appear. This is in lab frame. Huh? To analyze in center of mass frame, we should know velocities of colliding bodies in center of mass frame. So I'll proceed like this. Initial velocity of first body with respect to center of mass. So it should be U1 minus UC. U1 is how much? U. Velocity of center of mass, U by 2. U2C should be equal to U2 minus UC. What is the initial velocity of second body? It was at rest, no? You can see from here, 0, U by 2. So in C frame, how the system will appear? In the C frame, the same system will appear. The first object will be moving with a velocity U1C, and the second object will be moving with a velocity U2C. Where we are doing in the C frame. So I think we have to put box like this. And in what direction the C frame is moving? In this direction. We'll calculate momentum with respect to center of mass. Initial momentum with respect to center of mass. M1 U1C minus MU2C. And what are U1? So they should be equal to 0, no? So in ground frame, 2 is at rest. 2 is at rest. And 1 is approaching it. After collision, what happens? 1 will come to rest and 2 will move with the velocity of the 1. But in center of mass frame, what happens? They are approaching each other with the same speed U by 2. They'll collide. Okay, after collision, let's see what will happen. Till now, this is after collision. After collision, we have this is diagram. This is after before collision. Before collision in C frame. After collision, so we'll calculate this one. U2C is equal to U2 minus UC. What is value of U2? U2 is U by 2. What about U1C? U1, oh, so okay, this should be V, no? Let me retain the symbols, it'll be easy for you. So V1 means final after collision, no? We are discussing. So V1 minus VC. What is V1? 0. This is U by 2. Look at that after collision. So how in the C frame, how the situation will be? So we'll put the box. And that box is moving with a velocity U2. There is the velocity of center of mass. Then this will and this will be the center of mass. This will be moving with a velocity V1C. This will be moving with a velocity V2C. After collision in C frame. Okay, look at this. After collision in C frame. So in the C frame, what will happen? The two objects will come collide. Where they collide? At center of mass, and they will move away. What about the speeds? Will be same. In C frame, both will come and collide with us. Both will approach with the same speed, collide, and after collision also, both will again move away with the same speed. Then what is the momentum with respect to center of mass? In C frame, we'll calculate momentum. How much it should be? M V1C minus M V1C plus M V2C. And magnitudes are equal. So now shall we say momentum with respect to center of mass? Always 0. This is very, very important. Momentum with respect to center of mass will always be 0. You take off any system. I think already in center of mass chapter, I just gave one examples. Momentum with respect to center of mass, always 0. I think this is the very important thing which will help us to solve some of the problems. If you take some pathfinder, no, where if you solve the problem in C frame only, you can get the answer. Otherwise, not possible in lab frame. Lab frame, it will become very lengthy. C frame is what the int for that problem. When we go for 2 dimensions, no, you can see that the collisions in lab frame very lengthy, lot of mathematics, very complicated. In C frame, it will be very systematic and very simple. But in our syllabus, maximum we'll discuss problems on on lab frame only. The 2-dimensional collision better to learn in C frame. It'll be much easier than the lab frame. 1-dimensional collision, okay, lab frame is advisable. Straight away will get answers. 2-dimensional collision, it's a C frame is what going to help a lot. I'm giving the best information on this one. 1-dimensional collision, take lab frame. 2-dimensional collision, better do in C frame. It'll be very easy for you to analyze the problem and very easy and flexible also. Better, I'm using word flexible, means less mathematics, you can get the answers very easily. So momentum with respect to center of mass, always 0. Shall we put it? So in C frame, what actually happens? Bodies, it's not a general for this situation. I'm bringing up bodies approach center of mass before collision. Next, bodies move away, approach or race, move away, you write it. Move away from center of mass. For this problem, I'm just giving the description. Then momentum with respect to center of mass is always 0. Not may, is I'm bringing. So this is also going to help us a lot, no? So you know momentum with respect to center is always before collision 0, after collision 0. During collision also will be 0. Momentum with respect to center of mass is always 0. So in the lab frame, one will come, two is at rest, one will come, collide, and after collision. So in the lab frame, what is the sequence? Two is at rest, one is moving. After collision, one will come to rest, two will move. In the C frame, what is the thing? Both will approach center of mass with the same speed. They'll collide, and where they collide? They collide at center of mass, and they will recede away with the same speed. And momentum with respect to center before and after collision will be 0. That's what it's telling here. Now you look at again kinetic energy in the lab frame, kinetic energy in C frame. Kinetic energy in C frame should be minimum, what we have already concluded in center of mass chapter. So you can, this C frame analysis you can do for any collision, elastic, inelastic. It's not that only for elastic collision, sir, you are doing, need not. You can do for any frame. Okay, now you check it. What happened the momentum? So you can ask, sir, how you conserve momentum? I give roughly the diagram, sir. Now it's very easy. What happened the velocity of center of mass before and after collision? This is some very important thing is what I'm trying to put forward. What happened the velocity of center of mass before and after collision? With what velocity center of mass was moving before collision? After collision also it will move with velocity of center of mass. Means you look at only center of mass. Don't look anywhere. Look at only center of mass. Will you feel any collision occur? Nothing, no? You feel as if nothing happened. This blocks will come, collide, and again this will situation. But you look at only center of mass. Is there any change in velocity of center of mass? Nothing, no? So you look at only center of mass, what you feel? The center of mass just continued its uniform inertia of motion. As if nothing happened. So if there is a no net external force acting on system, am I right? Because velocity of center of mass didn't change. Go back to center of mass. If the velocity of center of mass remains constant, what does it mean? Net external force 0. Net external force 0. So here also depend. Though the forces acted during collision, but net external force is 0. If net external force 0, then I'll conserve momentum. There's a reason why I'm conserving momentum. Whose help I'm taking? From center of mass. Because now you may ask me the very first thing, no? You may ask me like, sir, on what basis are you sure that these two forces will be equal and opposite? That's all, no? There's a very best question student can ask a teacher. On what, like how can you say that this JD and this JD will be equal? They may be different. Means what this body will exert force, it may exert other force. Newton's third law will not permit, but nothing wrong in thinking. A student can think, no, sir, here force 10 Newton, here 8 Newton. Let it be different. What's wrong? Because you said the body will undergo deformation. Some elastic forces will come here, this one. So I'll assume different. No, you can't assume different. So what the center of mass is telling, the net force acting on system is in fact 0 during collision. The reason for that, the velocity of center of mass remained constant. If velocity of center of mass before and after collision were not equal, then I would have said net external force acted on system. Okay, got this? So what is the conclusion now we can make it? As VC equal to UC. So therefore, net external force acting on system is 0. Therefore, you have to conserve momentum. So why we have to conserve momentum? There's a reason. Due to collision, the velocity of center of mass didn't change. So therefore, net external force 0. So therefore, momentum is conserved. Got the idea now? So actually, I should teach this one. Because you don't have any of idea this no momentum, all this, how you sir V2 equal to you. That's why I just superficially I just